So far in this unit, we've looked at how to calculate delta H in two ways. We've used bond energies and we've used calorimetry experiments in order to find the delta H for a given reaction. In this lesson, we're going to look at the final two ways of calculating delta H. We're going to use Hess's law and we're going to use heats of formation. These are connected to one another because the heats of formation formula that we will use is really a simple application of Hess's law. Hess's law uses the fact that enthalpy is a state function. And you'll remember that enthalpy being a state function means that it's the initial and the final states that matter, the beginning and end that matter, and the pathway that we take to get from the beginning to the end is irrelevant in terms of calculating the delta H. If we look at this example here, we've got two different pathways to the same reaction. Reaction 1 and reaction 2 are actually two steps to complete the reaction that's discussed in reaction 3. So let's look at this for a minute. Sodium hydroxide, a solid, dissolving. The heat of solution for this reaction is negative 43 kilojoules. So 43 kilojoules is released in this process. The reaction between sodium hydroxide solution and hydrochloric acid solution is an acid-base reaction with a delta H value of negative 55. These two reactions are really added to produce this final reaction, but we could do this third reaction on its own. So in an experiment, we could do reaction 1 and reaction 2 and find their individual delta H's. We could then also subsequently find the delta H for this reaction, where we react solid sodium hydroxide with aqueous hydrochloric acid to produce the sodium chloride and water. The delta H for this reaction is negative 98. If you look at the values, this plus this is equal to negative 98. So really, these two steps are equal to this one-step reaction. And if we look a little bit more carefully, we can see that when we add these reactions, the way that we've learned in the past, okay, they add the way that we would expect. And what this is showing us is that the pathway that we take to find the delta H does not matter as long as the overall is the same. Okay, so when I add these two reactions, what ends up happening is the sodium hydroxide aqueous ends up simplifying, and what I have overall is a reaction between sodium hydroxide solid and hydrochloric acid to produce the sodium chloride and water. So reaction 1 plus reaction 2 is equal to reaction 3. And the delta H of 1 plus the delta H of 2 is equal to the delta H of 3. And this is because delta H is a state function. If we think about it even closer, we can see that this reaction really occurs in these two steps. So when we react solid sodium hydroxide with a hydrochloric acid solution, what ends up happening is the sodium hydroxide dissolves and then the dissolved sodium hydroxide reacts. Okay, so no matter which way you look at it, reaction 1 plus reaction 2 is equal to reaction 3. So if we can add 2, 3, 4 reactions, we can find the delta H of the overall reaction. And perhaps what you see developing here is a skill that we've already used before, where we combine reactions and add them to produce a goal reaction. We manipulated the initial equations in order to make them add up to a final reaction. We did this when we were working with K, and we wanted to find the equilibrium constant for an unknown reaction. We manipulated some initial reactions and then added them to equal our final reaction. And there were rules associated with the manipulations that we did. Our discussion below shows us that when we add reactions, the delta H's simply add up. This is different from the equilibrium constant rule, so you need to keep that in mind. Now, the other manipulations that we do when we're performing Hess's law or applying the law of additivity is we could end up needing to flip a reaction around. If we flip a reaction, so for example, if we wanted to flip this reaction around, it would change the sign of the delta H because a previously exothermic reaction, where energy is a product, would become an endothermic reaction where the energy is a reactant. These are a little bit more intuitive than the rules we had for the constant K. The other manipulation that we might need to do is to multiply a reaction by some value x. To understand what the effect on delta H is, we need to remember the relationship between the delta H and the balanced chemical equation. The delta H for a balanced chemical equation is consistent with the mole ratio in the balanced chemical equation. So for example, the negative 43, the 43 kilojoules released occurs when 1 mole of sodium hydroxide is dissolved. So if we changed this and had 2 moles of sodium hydroxide dissolving, then the amount of energy that we released would be double. Because whatever we do to the equation, the same is going to apply to the delta H value. So this kind of question will look familiar. We want to find the delta H for a particular reaction using a certain set of reactions that have known delta H values. So you'll recall that we look at our goal reaction and we make decisions about what manipulations we need to make on the given reactions. Ultimately, we want 2NH3 in our final reaction. So when we look at the second reaction, which has a 4NH3, that tells us that we're going to need to divide that reaction by 2. Because the O2 is found in all of the reactions, it's not going to be all that helpful in making decisions about the manipulations we need to make. So we'll skip over that one and look at N2O. For N2O, we need it to be a product with a coefficient of 1. So this final reaction needs to be manipulated by dividing it by 2 and flipping it. To get the 3H2O as a product, you'll see that we need to divide the second reaction by 2, and we've already made that decision. At this stage, we've gone through all the reactants and products, and we haven't made any decisions about the first one. And rest assured, they're not going to give you a reaction that is useless. So what we're going to do is just leave that and see how it's going to be useful to us in a couple minutes. Okay, so we're going to write out what we have. We've got 2NH3 plus 5 halves O2, 2NO plus 3H2O. And with these, you'll notice that the states are given. Okay, it's really critical that we keep the states in mind because only compounds with the same state will be able to simplify one another. All of these are gases, so I don't need to write out the gases, but I do need to constantly be keeping in mind the states of the reactants and products. Because I divided this reaction by 2, I divided all of the coefficients, and the delta H also needed to be divided by 2, because if I use half the amount of moles, I'm going to release half the amount of energy. But the sign didn't change because it remains an exothermic reaction. For the third reaction, I need to flip it and divide it by 2. So I get 2NO2 goes to N2O plus 3 halves O2. In this case, I need to change the sign and I need to divide it by 2. Now, a few things to note when you're dealing with these. The signs when you're doing the computations are really important, so I would recommend that you are deliberate about the signs so that you don't forget them. And what you're also going to find is that you're going to end up with fractions for oxygen. Okay, you can put that in a decimal if you want to put that as 2.5 and 1.5, that's fine. Now, if we tried to add these up, it would not add to this final reaction because we have some extra materials that actually need to be removed. And that's what this third reaction is going to help us to do. You'll see that there is NO in this reaction, but there's none in the final reaction and nothing in this second one to cancel it. But if you look to the first reaction, you can see that if I just leave it, 2NO plus O2, that's going to simplify the 2NO. And it's also going to simplify the 2NO2 that I've got here. So this is one of the more challenging additive reactions involving an extra reaction that's used to cancel things out rather than to actually obtain the reactants and products that you want. Okay, so we can see the 2NOs simplify, the 2NO2s simplify, and the oxygens here, we've got 7 halves on the left-hand side and 3 halves on the right-hand side, which leaves us with the 2 oxygens that we're supposed to have. Okay, and as expected, the reaction adds up to our reaction that we were trying to determine. And when we take these delta H values that we've worked on, we're going to find that we get a value of minus 552.5 kilojoules. So this is how you find the delta H using Hess's law. I'd encourage you to pause the video and work on this problem. The delta H that you should obtain for this reaction is 226.7 kilojoules.